Here's a diagram of the Bernoulli apparatus that we used, or that you used in the experiment. And let's see what Bernoulli's equation tells us. Bernoulli's equation and the continuity equation tell us about the situation that we see here. We have a state 1 where the pressure is 1 atmosphere, and the height we're going to call delta H. Whatever altitude you observed for the water in the first tube is your delta H. And the velocity of the water at this point is approximately 0. Now actually for this tube, if you measure the velocity here, it's not completely negligible. Of course the water's turbulent here, but that's in all directions, but there's still a net velocity in this direction. Water will empty out of this tube rather quickly if you stop letting water flow into it. Still, we're going to make the assumption that the velocity is approximately 0, and as long as we have fairly narrow tubes down here, that's still a good approximation. We assume a diameter D1 here and a diameter D2 here. We look at the vertical tubes, and hopefully you found a way to make these things stay vertical. But we look at these vertical tubes here, and we see that this one is fuller than this one. And there's some distance, delta Y, between the water level in this tube and the water level in this tube, which hopefully we were able to observe. Now we have a state 2 here, where the pressure is 1 atmosphere, the altitude is 0, and there's some exit velocity. That exit velocity would be predicted by Bernoulli's equation or by potential and kinetic energy considerations to be the square root of 2g delta H, where the delta H is the height of the water column here relative to this point. Now we know that when we actually perform the experiment, the exit velocity will be somewhat less than this due to turbulence and frictional losses of energy. Bernoulli's equation is going to overestimate reality a little bit, because remember, Bernoulli's equation is an ideal equation where there's no dissipation of energy and so forth. Okay, so in any case, this is what we get for the exit velocity, and of course we can analyze that using Bernoulli's equation. State 1 here, state 2 here. In state 1, the velocity is 0, so this term's 0. The pressure is 1 atmosphere. In state 2, the pressure is 1 atmosphere, so we're going to be able to subtract those pressures. And the height at state 2 is 0, so this term's going to be 0. After we subtract the 1 atmosphere from both sides, we're just left with 1/2 rho V2 squared equals rho g delta H, with the solution V2 equals 2g delta H, and that's no surprise. This is almost identical at this point to what we get from the energy considerations, the potential and kinetic energy analysis. Now let's look at what's going on in the tube. We're going to assume that the velocity in the second tube is in fact the square root of 2g delta H, even though, as we've seen from predictions of Bernoulli's equation, it's going to be a little less than that because there's energy dissipated. We don't get quite the velocity that we predict. Okay, let's look in a little closer here. Okay, here we've got a diameter D1, here we've got a diameter D2. We've got the velocity V2 here. V1 must then be in inverse proportion to the square of the diameter, or the inverse proportion of the areas to velocity V2. Since the diameter here is D1, which is greater than D2, our D2 over D1 ratio is going to be less than 1. We're going to square that and multiply it by V2, and that's going to give us our velocity here. Okay, that follows from the continuity equation, follows from simple consideration of those volumes that we looked at last time. And of course we can set that up with the continuity equation. These are supposed to be velocities, not volumes. From the continuity equation we can get V1 over V2 equals A2 over A1. Ratio of the velocities is inversely proportional to the ratio, or the inverse of the ratio of the areas. The ratio of the areas is just the square of the ratio of the diameters, and we get the equation that we used up here. We get the result that we used up here. So now we have an expression for velocity V1 in terms of velocity v2, which is expressed just in terms of delta H. As long as we know how high the water is in that first tube, that tells us delta H, which gives us our model for v2. And if we know the two diameters, then we can get our v1. Now let's think about what's going on with these small, hopefully vertical tubes. Okay? We see that there's more water in this tube than there is in this tube. There's a difference delta Y, which implies a pressure difference rho G delta Y. Okay? Now, this tells us that the pressure at this point in this fluid is less than the pressure at this point in this fluid. Now the pressures at these points, the water along the wall really isn't moving very fast. The pressure at this point is the rho GH, where H is the depth here. The pressure at this point is the rho GH, where H is the depth here. Now in the pipe, H is more or less constant. At least the average depth is constant in the pipe if we were able to hold the system in a horizontal configuration or horizontal orientation. It follows, since H is constant, that your kinetic energy and pressure terms are going to have the constant sum, which means that there's greater pressure in the larger pipe. Since the velocity here is greater, the pressure here is greater, which is consistent with what we see here. And the difference in the pressures should actually be the same as the difference in the water levels here. That is, the change in the difference in the pressure should be your rho G times this delta Y. So kind of summarizing what we have at this point, pressure difference between here and here, therefore the pressure difference between here and here is rho G times this delta Y. The velocity 1, the velocity in this tube is the exit velocity, which is what we called V2 a minute ago, times the square of the ratio of the diameters, so that the pressure differential between here is 1/2 rho V exit squared minus 1/2 rho V1 squared. Now we've got expressions for these velocities, so that we should be able to find our delta P here. And this delta P should be consistent with this delta P, and we'll see how that works in the next clip.